All right, future pharmacists, let's get right to it. You know that a drug is completely useless if it's stuck inside its own tablet. Today, we're not just running a test, we're going to simulate that critical first step in the human stomach. This is the in vitro dissolution test, and we're using nitrofurantoin as our model.
And that quote right there, that's the whole game. It really is that simple. A solid pill can't do a thing for a patient until it dissolves. It's the very first hurdle a drug has to clear, and for a lot of them, it's also the highest.
And that really brings us to the core of our topic today, a problem so fundamental we can call it the dissolution dilemma. So what is dissolution, really? At its heart, it's simple. A solid breaking down and spreading out into a liquid. For every single tablet or capsule you will ever dispense, this has to happen first. The drug molecule has got to escape its solid prison and get into the GI fluids before the body can even think about absorbing it.
But here's the thing. This isn't an equal challenge for all drugs. Some dissolve in a flash, no problem. So the big question is, for which drugs is this one little step the absolute make or break factor that decides whether the medicine actually works?
Well, the answer comes from a super powerful tool you should definitely know by now, the Biopharmaceutics Classification System, or BCS. This whole framework gives us the scientific reason why a test like this is so critical for certain drugs, including the nitrofurantoin we're looking at today.
The BCS framework basically sorts drugs into 4 buckets based on 2 really key properties. First, how well they dissolve, that's their solubility, and second, how easily they can pass through the intestinal wall, that's permeability. A class 1 drug like metoprolol is the dream scenario, high solubility, high permeability. It dissolves easily and gets absorbed fast, but we're here to talk about the tricky ones.
Okay, now what I want you to really focus on here is what class 2 and class 4 drugs have in common. Take a look. Their permeability is different, but they both share the exact same weakness, low solubility. These drugs really struggle to get into solution. They're kind of the problem children of oral medications. And yep, nitrofurantoin is one of them. And this is where it all clicks. For these drugs that don't dissolve well, it doesn't matter one bit how great they are at crossing the intestinal wall if they can't even get into solution to begin with. So for them, dissolution isn't just a step, it's the rate-limiting step. The speed of dissolution literally controls how fast the drug is absorbed and whether it's going to work at all. So now that we know exactly why this matters so much, let's shift gears. Let's talk about how we build a test that faithfully mimics what's going on inside a patient. We have to create a truly biorelevant environment.
Before we even drop a tablet in, we have to establish something called a sink condition. And let me tell you, this is absolutely non-negotiable. It just means our testing liquid can hold way more drug than what's in our tablet. This is key because it mimics the body, where the bloodstream is constantly whisking away absorbed drug, always making room for more to dissolve.
For our test, we're using the industry standard, the USP Apparatus 2, which you probably know as the paddle method. And our liquid isn't just any water. We're using 1 full liter of artificial gastric juice, which is specially made to simulate the acidic environment of the stomach. First up, temperature. We lock our water bath at exactly 37 degrees Celsius. Why? It's simple. That's human body temperature. If we use any other temperature, our results are basically useless from a clinical standpoint. Second, we need movement. The paddles are going to rotate at a nice, steady 50 revolutions per minute. Now that's not just some random number. It's carefully chosen to simulate the gentle, constant churning motion you'd find inside the stomach. All right, the stage is perfectly set. Our environment is biorelevant. Now it's time for the main event. Let's walk through how we capture the data step by step. The process here is all about precision. We drop 1 tablet in and bam, the timer starts. Every 10 minutes on the dot, we're going to carefully pull out a 5 milliliter sample. And this next part is critical. You have to immediately replace that volume with 5 milliliters of fresh, pre-warmed media to keep our total volume and sink conditions perfectly constant. But hold on, we've hit a really common problem. The amount of drug in that 5 ml sample is way too concentrated for our UV spectrophotometer. Remember Beer's law? It basically says that absorbance and concentration are proportional, but only up to a certain point. Our samples are so concentrated, they're way outside that linear range, which would give us completely garbage data.
So what's the fix? Well, it's simple, elegant, and absolutely essential. Dilution. We take exactly 1 milliliter from our sample, put it into a 10 milliliter volumetric flask, and fill it up to the line. This gives us a perfect 1 in 10 dilution, which brings our concentration right into that sweet spot for analysis. And that number, 10, that becomes our magic number, our dilution factor for the final calculation.
Okay, so we've got our samples, we have our raw numbers from the machine. Now comes the fun part. Let's do the math and turn all this into the actual story of our drug's performance. So each one of our diluted samples gets its turn in the UV spectrophotometer. We measure its absorbance at the specific wavelength for nitrofurantoin, which happens to be 370 nanometers. And that gives us our raw data point, a single absorbance value for each time point we sampled. Now for the analysis. First, we take that absorbance value and use a standard curve to turn it into a concentration, usually in micrograms per milliliter. But, and this is key, that's the concentration of our diluted sample. So next, we have to multiply by our dilution factor of 10. Then we multiply that by the total volume of our media, 1,000 milliliters, and that gives us the total micrograms that have dissolved. One quick conversion, and we've got our final answer in milligrams.
Look, this whole process isn't just about crunching numbers to pass a lab. Every single step we just took, from setting the temperature to the final math, is all about generating one single, powerful piece of clinical evidence. So let's see what this curve we're creating really reveals, and why it matters so much when you're standing behind the pharmacy counter.
And here it is. The final result of all that work is the dissolution profile. It's a simple graph that tells a powerful story, plotting the percentage of drug released over time. It shows you visually both the rate and the extent of dissolution. And this is its most important job. This profile is the key evidence used to establish bioequivalence. For a generic drug to get approved, its dissolution profile has to be virtually identical to the brand name drug. This curve is the proof.
So the bottom line is this. When you look at this graph, you are not just looking at data points. You're looking at a promise of therapeutic equivalence. It's the guarantee that the generic medication you hand to your patient is going to work just as safely and effectively as the brand name they might be used to. The accuracy you bring to this lab directly translates to patient safety.
Every single prescription you will ever fill is an act of trust. Your patients trust you. They trust that the pill in that bottle is what it says it is and that it's going to do what it's supposed to do. This graph, this curve, is the scientific foundation of that trust. It is a promise of quality. So as you go into the lab, the real question isn't just about getting the right numbers. It's about upholding that trust. Is that a promise you are prepared to keep?